All right, welcome everyone. Exploring machine learning on Heroku. Certainly everybody is excited about this space. We're going to be talking about building custom apps with PredictionIO. So first, of course, we have our forward-looking statement. What I'm going to be showing you today is a open source project that is not a, what is officially supported here is the Heroku runtime. What we're going to be showing, PredictionIO, is software that you elect to run on our runtime. So we're here to help make this the best experience possible, but please keep in mind that those of you who purchase our services, make sure you make purchase decisions based on the features that are currently available as generally available features. All right, so with that out of the way, I'm Mars Hall. I work at Heroku. Have been working on this machine learning with our platform for about a year now. And so essentially what I'm going to share with you today is what we have figured out how to productionalize machine learning on Heroku. And so when we say machine learning, really the nexus of this is that normally when you write software, you write code or you use some declarative stuff, but you essentially describe exactly what you want the computer to do. So with machine learning, instead what we're doing is we're writing software that's going to take data in order to build a model for how to actually run and execute. So it's a big difference here. It's kind of like we're guiding how the machine works as opposed to telling it exactly what we want it to do. And Heroku, of course, is Salesforce's platform as a service. It's a cloud that helps you operationalize applications. So specifically, we're targeting PredictionIO on Heroku to enable data scientists and developers to build custom machine learning services. So this is using Apache PredictionIO. So PredictionIO, it was acquired by Salesforce a couple years ago and donated to the Apache Software Foundation. And so PredictionIO itself is essentially a framework to help you write custom machine learning services. Now, of course, there's a lot of templates and guides and ways that you can leverage what other people have contributed in order to build your machine learning service. But fundamentally, PredictionIO is about building really any kind of ML service you want. So what it really provides is a systematic workflow to reduce the amount of development and operations overhead of working with machine learning. So the stack of software that we actually are talking about here today, this is Apache PredictionIO on Heroku. So you're going to be working with the Scala programming language. This is a language that works with the JVM, the Java Virtual Machine. It's part of a really stable ecosystem. It's a beautiful language. As you get to know it, I have learned it specifically for this project over the last year, and I can say that yes, it's got its challenges, but it's definitely worth it. It's really good at solving these problems. So Apache Spark is the underlying distributed data processing application service that PredictionIO essentially wraps and helps you run. So coming with Apache Spark, you get the Spark machine learning and MLlib libraries. And so these libraries give you well-known algorithms. You could think of it as a standard library for solving machine learning problems. There's lots of other kinds of algorithms that you could use, or of course you could create your own, but Spark comes with this package of really great things from classifiers to regression engines, clustering, like all different kinds of problem spaces. So these pieces of software are going to be automated with the Heroku Buildpack. So this is going to help us automate our local setup of PredictionIO as well as deploying it to Heroku. And so once again, Heroku helps us minimize the amount of server jockeying work you have to do. Because jockeying with servers is not where you're going to win. So what we want to do is help you avoid the risk and complexity that frequently data science work brings and let you focus on building great machine learning apps. So these build packs that I'm talking about at Heroku, essentially you could think of them as plugins or extensions that allow you to build and run all different kinds of languages on the Heroku platform. So here is a tile of our 9 supported languages. That's Node, Python, PHP, Ruby, Java, Go, Gradle, Scala, and Clojure. So the fact that we have a PredictionIO build pack, it actually leverages that Scala build pack under the covers, and we extend it in order to support the data science workflow that PredictionIO provides. So this build pack helps us install and configure dependencies, compile the Scala source code, import data, train the model, launch the web process. This is a whole workflow, which is better explained in this diagram. So you can see a more detailed version of this on the PredictionIO build pack GitHub repo. I highly recommend, if you have any questions, want to dive deeper, basically everything I talk about here today is linked through that build pack repo. So basically, PredictionIO will take the engine source code, so the Scala source code, and combine it with the pre-existing open source libraries. These are Spark, SparkML, the Postgres database driver, all the different aspects of the code that you don't have to write. You're going to be leveraging all these other open source pieces. And the build process creates an executable engine. So at Heroku, we call this a slug. And that slug is something that on the Heroku platform can very quickly be loaded into servers so that you can spin it up and run, whether it's a console or a web process or a training process. That executable engine becomes this reusable, quickly executable cloud application. And with that, in this release process, we give you hooks to help load and synchronize data into the PredictionIO event store, as well as, of course, training the model on that data. And that trained model gets saved to a database or to S3 file system so that when the web process starts up, it can serve real-time REST queries for predictions. So this sounds pretty technical, I know, and it is. This is for data scientists and developers. And so as I mentioned at the beginning, I also started my path on this about a year ago. And so I would say don't feel daunted about diving into this. There's a lot of different skills that you will build in the process of learning this stuff, but machine learning is so valuable today that it's definitely worth it. So probably the highest, most general talent, skill you're going to need is applying machine learning algorithms and statistical evaluation techniques to create a desired outcome. So that might sound complicated, but the thing is, if you're trying to solve these problems for a business use case, you can't just guess that it's working. And so you're going to have to become very methodical, scientific about feeding data into your engine, evaluating those results, and tuning your engine or changing the algorithm in order to get the kind of results that you want. And PredictionIO will help you do this using its DAYS framework. So this is the part of it that's in Scala. DAYS stands for Data, Algorithm, Serving, Evaluation. And these are the main hooks that the framework gives you for plugging into this machine learning workflow. Then also, when you're working with PredictionIO on Heroku, our first-class data store is Postgres. You can use Heroku Connect to synchronize data over from a Salesforce org. So this is your avenue to getting Salesforce data into a PredictionIO engine. But there's still a custom step. Anytime you want to implement one of these engines against your Salesforce data, you'll still have to actually write a connector in order to take the data out of the Heroku Connect database and transform it into the format and the database schema that your given algorithm requires. And so this is going to be SQL focused using Postgres. And then finally, probably the easiest part of all this is deploy to Heroku. So deploy to Heroku requires some Git skills, requires understanding the terminal, and using the Heroku CLI. But what do you get when you start working with all of these different pieces? Suddenly, your data science workflow can become agile, right? You can actually collaborate with other people. Heroku itself gives a great team interface for the actual operations and management of your applications, as well as the built-in GitHub integrations that help you be able to collaboratively like branch an engine, try a different algorithm, push it to an environment at Heroku, see how it works, share the results with your team. This is honestly, from all the data scientists I've talked to, this is kind of a panacea because it's normally such a custom environment to do custom machine learning. And so this really helps you be able to step beyond all of those arduous tasks of just making it work. Then we also have Heroku's continuous integration, which is built into pipelines. And our PredictionIO Buildpack does have test pack support, so it will work with continuous integration pretty effortlessly. So with Heroku, you also get horizontal scalability of your web dynos and Spark executors. This is not so much agile as it is just saving you a lot of time when you start needing to solve a lot of real-time queries. You can easily scale up the PredictionIO web process and serve hundreds or thousands of requests per second. All right, so let's take a look at a few aspects of PredictionIO in action. So I'm really excited this will be the first demo of our local dev experience. So one of the things, actually before I go into that, so after local dev setup, we're going to touch on two different engines, a classification engine and a recommender engine. So local development is something that can be very challenging, especially for a beginner with a new piece of software, because suddenly you're asked to like download all these pieces and put them in certain places. And in this case, it's a JVM-based system. And so if you were to go to the PredictionIO website and go to their main install page, you're going to see a bullet list of all the dependencies that you need to figure out how to install. And while that kind of bar of entry is pretty normal, I think, for a lot of complex Java projects, it's really not ideal, you know? And so what we have done is we want to help you be able to use your personal computer to create or customize an engine. And the real value of this is that when it's running on your local computer and not Heroku, you can quickly iterate. You can make a change to the code, do a rebuild, and within, depending on the type of change you've made, in under a minute, you can actually evaluate your changes and see how it's working. And so once you've made some changes, you do a git commit, and then you can push to GitHub and or Heroku, depending upon how your deployment is set up. So for this local development, we have enhanced the Buildpack to help you. So this is a little bit different. If you all are familiar with Buildpacks at all, you may find that many of them don't really give a local development experience. It's more up to you to install Node or install Java and make sure that you've got all the right things in place. But in PredictionIO's case, it's a complex enough install that has enough variances that honestly, people that are experienced with it can get into complicated trouble because you have inconsistencies. Like you don't realize what version you have for one engine versus another. So by using the Buildpack, we're going to help you install PredictionIO locally for each engine individually so that you have the exact same dependencies locally as when you deploy to Heroku. And that includes how we configure the app. So we use environment variables stored in a .in file locally. This is another pretty normal thing with Heroku, as Heroku uses this config variable, environment variable system to configure apps. So let's actually take a look at what local development looks like. So if you visit the PredictionIO Buildpack, you'll find, I'll go back to the first page. So you'll find that there's a lot of information here, and down here at the bottom we have a link to local development. And so in this case, I'm not going to go through these steps with you, but we're just going to step right to the point where I'm doing the main local development steps so you can see what it's like. So this is in the terminal, and I have already run this because it downloads a few hundred megabytes worth of jars and Spark and PredictionIO. But here you can see when I run this bin local setup command, it goes through and installs right here into this local PredictionIO directory. It installs PredictionIO, Spark, Postgres. It sets up our configuration files. And what it delivers us is this bin pio command. And so with bin pio, I'm able to run the status command, and this is like a canary for the current runtime of PredictionIO. This tells you, hey, are things like set up such that it seems like it's going to work? So we can see that PredictionIO is installed, Spark is installed, and most importantly, we can see that our storage sources, all three of them, are verified to work. So with that in place, we can use the other pio CLI commands, like build, in order to actually do, so PredictionIO provides this CLI, this pio command, where you do pio build, pio train, and pio deploy in order to run a web process. There's a number of other helper functions in there that do all kinds of stuff for you, but those are the primary ones. And so as you can see, I just rebuilt this engine, and it's ready for training. So at this point, locally, I could do pio train, but due to time constraints, I'm not going to have you all watch that happen. All right, so that's basically what it takes to get the local dev going. So now let's talk about the classification engine. So you might have seen this demoed out at the Einstein machine learning booth, after which I will be hanging out around that booth, by the way, to take questions. So this classification engine is an example that we have on our Heroku GitHub. And classification is a really great use of machine learning. It helps you to categorize things based on attributes. So this is a type of supervised machine learning. And what that means is that the data that we feed the algorithm in order to build the model essentially has like the questions and the answers. So we train the engine by feeding it, you could think of it as criteria for whenever you see this, answer this. But the smartness of an engine like this, the random forest decision trees algorithm in this case, is that after you've trained it, it's going to be able to answer these questions for you for data that it hasn't seen before. So you train it, but then it will figure out, of course, how to answer questions for combinations of properties it hasn't seen before. So the beautiful thing about supervised training is that you can build a viable model with a small amount of data. So because you are feeding this machine learning engine only accurate, known data, you are able to very much craft how it provides answers. And of course, more data will mean that it can build a better, stronger model that perhaps covers greater data ranges. But it's a great point that it doesn't require as much data. So let's actually take a look at our classification demo. So once again, this is on GitHub. It's linked off of the Buildpack. And I want to point out that here in the README, we've tried our best to document this really well. Here's a link to the random forest algorithm. You can go and read about how this works, comparable algorithms to it. It's a really fascinating internet hole to go down one evening late. So let's take a look at what this engine really looks like. So earlier, I talked about the PredictionIO DAYS framework, data, algorithm, serving, evaluation. So since PredictionIO is a framework, And this is that PredictionIO engine classification repo I've actually cloned here. You can see that our main code is here in this source main Scala file. And here we've got a data source. We've got our, where's our random forest algorithm? So that's the D and the A. We've got the serving class, and we've got an evaluation class. So the other things that are there are also great pieces of the framework and auxiliary pieces to this engine. But let's take a look at data source, which this is the first thing you're going to have to address if you want to build a PredictionIO engine for your own use case. So the data source, because this is a framework, what we're actually doing here is we're extending the built-in data source that PredictionIO provides. We're making our own instance of it. And in this case, the main method we care about is read training. And so in this function, this is where we write the code to tell PredictionIO, in this case, use the event store and select entities that are users with a service plan and voice usage, data usage, and text usage attributes. So you could imagine, if you have all these different attributes for your customers or accounts, you're going to be coming in here and revising exactly what data this engine selects in order to train on. And then in this case, for this particular algorithm, what we actually create are these labeled points that contain vectors of these numeric values. Exactly what the training data looks like is going to vary from algorithm to algorithm because they're all unique and different. But that's part of the interesting way of learning, how each engine really works. So what we end up returning is this training data containing the labeled points. And so if we hop over to algorithm, you'll see that once again we're extending an algorithm that is built into PredictionIO. So that gives us it provides essentially a lot of functionality to enable this workflow that we don't have to write. Instead, we're able to focus right in on this train method. And so in this train method, you'll see that we get the data. And this is a relatively simple engine. All we do is we use the random forest algorithm, and we call train classifier, and we pass it the data points along with all of our parameters. And all of these parameters are actually set up in our engine JSON file. I know I'm going through this fast, but I just want you all to get a sense for kind of how these main pieces are laid out. And so in this algorithms file, you'll see that we declare an algorithm and we have these values. And these values, I did not actually pick. I used a whole nother process in PredictionIO, the evaluation step, to actually iterate through training in hundreds of different ways with all different combinations of these parameters. And PredictionIO helped me pick the one that provides the best, most accurate classification results. So let's actually see what this engine can do. So I have built this JavaScript React app, which uses a deployed version of this classification engine with its example data. And so that example data is a very small amount of data, and the main aspects we're looking at here is a mobile phone user account with a certain amount of voice, data, and text usage. And so as I move these little dials, you'll see up here that it makes a prediction. So this is in real time calling out to my PredictionIO query interface. And so as I change this value, you'll see eventually, okay, somewhere around here, our training has triggered it to switch to the more data plan. And if I add some text usage to it, I'll keep adding more text, and eventually I enter a data and text plan. That makes sense. And same thing, if I add voice usage, eventually we'll get to more everything. And so it's actually been trained on 8 different service plans. You could imagine that you might have many more types of service plans, more classes that you want it to categorize. as well as the real power of this. When you look at something like this, you might say, well, I could write some procedural programming to just do some if-then statements and like figure out exactly the same thing. Well, what if you realized, oh, well, these like numbers aren't really telling enough. We need voice usage in the last 24 hours, in the last week, in the last month. Same thing for each of these metrics. We need to know, like, does this person roam? Do they have a family plan? Like, you might imagine you could build up this model using dozens or even hundreds of attributes. And of course, once you train the model, it's not stuck. Like, if you had manually written all those if-then statements, you end up in a world where you have to go and like figure out new logic as the trends of your service plans and data change. Of course, all we have to do with PredictionIO is train it on a newer window of data in a month or in a day or whatever, in a quarter, and then you get an entirely new model based on that newer data. All right, so that's a brief overview of classification. Now let's take a look at the universal recommender. So this is a really great engine. It's far more complicated, as you'll see in a moment, than that simple classification demo. It's more complicated because it's honestly far more sophisticated. It does a lot more in the custom code. And as we go through it, I'm going to try to point out some of the ways that this sophistication can help you solve some business problems. So a recommendation engine, it recommends things. And in this case, it's based on both history of like purchase events, bookmark events, rating events, and relationships. So this is where this algorithm that we use with this engine, the cross co-occurrence algorithm, really shines, because it builds up these matrices of correlated attributes to actions so that it can suss out these latent relationships in your data. But this is the challenge with unsupervised learning. So this recommendation engine is unsupervised. And so that means that when we train it, we don't tell it what we expect. We don't know at any given point, hey, when a user purchases this and this, I want you to recommend this. No, we want this algorithm to build up this network of understanding of relationships of our data so that it can find answers for us that we didn't know about. But the challenge with unsupervised learning is that to make a viable model, you need a lot more data. And you need a lot more data because you need to get good signal out of noise. So in order to build up those strong correlations that make good recommendations, you have to have enough history and enough data to actually enable it to rise those good recommendations above the noise of just kind of random correlations of things people happen to buy. So let's actually take a look at the universal recommender in action. So once again, Heroku GitHub repo, linked from the Buildpack. Here we describe exactly what it is, and we link to the correlated cross-occurrence algorithm, another really interesting architectural treatise to read when you have some spare time. So let's take a look at our data source and algorithm for the universal recommender. So we're not really going to follow this code because it does a lot more here. But you'll see that the read training method still queries the event server, gets users. The event names are abstracted. But in this case, for this engine, if we were to look at engine.json, you'll see that the events we care about are purchases and bookmarks. But once we get those events out of the database, you'll see that there's a lot of other processing that happens here. And that's because the folks who built this engine literally implemented the algorithm in PredictionIO. So when we talk about the cross co-occurrence algorithm, it's not like that random forest algorithm was, where it's just a function that you call in the Spark machine learning libraries. In the case of cross co-occurrence, it's actually all implemented here in data source, and there's quite a few different aspects here. There's a algorithm file, there's actually a whole model file, there's a popularity model, there's an Elasticsearch client, there's a lot of pieces to it. But what you get out of this data source is that we end up loading an RDD, which is a distributed data set of those purchase and bookmark events. And this fields RDD is essentially a distributed data set of every item's properties. So in our sample data set, this is like, our sample data set once again focuses on mobile phone type purchases. And so our items have fields like what platform they work for, what category of product they are, that kind of stuff. And then in the algorithm, you'll see that once again, we get the prepared data, but there's a huge amount of processing that happens in here. And so if you follow along in this PredictionIO, in this particular repo, you'll probably find that we're continuing to contribute to it. We're actually working very actively with this project, building a couple pilot projects to prove out its enterprise worthiness. So let's take a look at another demo. This is another React app that I created just to try to give a high-level interface of what's going on here. So I happen to know user ID 100 is in here. Let's pull them up. And what you're going to see on the left-hand side is the history of this account. So you'll see that they purchased an iPhone, and you can see the fields that are on here, the platform, the category, and the subcategory. And so as we scroll down, you'll see they purchased a health heartbeat tracker, a lightning cable, some headphones, a case, and onward. So what we get back from the recommendation engine is, of course, some hopefully good recommendations. It's recommending a high-speed lightning charger, a different case, Apple Care, and a pocket battery. But you'll see down here it's recommending an Android phone. And it's like, why would we recommend an iPhone person an Android phone, right? Well, that's because we've only trained this example engine with about 200 events. So there's not enough data to support the strength of the recommendations that we really want. Let's check out one more of these accounts. And you'll see, once again, this is an iPhone purchase. And you'll see that in this case, we're actually recommending another iPhone to them. So that actually brings me to a quick customization point. So if you have someone who's just bought something, why would you want to show more of that thing in the recommendations, right? This is a classic problem where it's like, I just bought this thing, stop showing me more of it. So the universal recommender gives you a really powerful real-time query interface. And if we jump over to, this is the JavaScript code behind my, that query, that React UI I was just showing you, you'll see the query right now is just a user ID. That's all I'm passing. And I just want it to give me all of the relationships it found for that user ID. But the universal recommender supports some really cool stuff. In this case, we're going to use field biases. So as you can see, I add this fields to the query. I say for the category field, if it contains the value phone, let's bias it to 0, which means we're not going to show it anymore. So I have this running locally. Let's make sure. Yeah, it looks like it's still up and running. And then I'm going to go to Chrome, where, as you can see, I've got this running on my local host. And I'm going to search for the same user, 102. And let's go take a look, and we'll see in the recommendations, headphones, a cable, another wallet, heartbeat tracker, another case. No more phones, though. So this is really powerful because although the trained model can't be changed that quickly, by altering your queries to the recommender in real time, like from your front-end app, you're able to very much customize recommendations to the real-time context and behavior of users. All right, so that was the whirlwind tour. So forward-looking with PredictionIO, what else are we doing? So I mentioned that we're doing a couple internal recommendation pilot projects. As we build up that understanding, we're going to share it out as a public reference for how to deploy PredictionIO with a Spark cluster in a Heroku private space. Also, we're working on more Heroku-optimized engine templates, so this should help you be able to get started more easily for more use cases, and also be able to compare and understand the ways that we make these work really well on Heroku. So if you have any feedback, any ideas, it would be great if you open up issues on our PredictionIO Buildpack. So that is a direct line to my team so that you can share with us like what you want to do. If you're trying to use it, problems you're having, or it's a GitHub repo, please feel free to open pull requests and help us actually contribute to it. So what have I given you a whirlwind tour of today? You can use Heroku for machine learning. You can create Spark machine learning apps with the PredictionIO framework. Our Buildpack enables local development and Heroku deployment. And you should get started with a Heroku optimized example by starting at the Buildpack. So I'm Mars. This was Exploring Machine Learning on Heroku. We have a few minutes for Q&A. And after that, I'm going to wander out toward the Einstein machine learning booth, where hopefully we can continue some conversations. Oh, and I forgot to mention, at 12 p.m., so that's just in a few minutes here, there's going to be a presentation about Heroku Connect and Postgres. If you are interested in connecting your Salesforce data with PredictionIO, that could be a really valuable session to attend because Connect is going to be your friend. Yes. We've got a micro. Oh, no more microphone?
I'll just speak loudly.
OK.
Oh, for recording purposes, yeah. It's easier than having to repeat questions. Morning. You had mentioned when you want to pull your Salesforce data into your training model. Sorry. That you need to transform it. Could you talk more about that?
Yes. So PredictionIO provides what is called the event store. And the event store is an immutable timeline of events. And so the concept here is that you can have many different systems that actually feed events into PredictionIO. And this event store uses a JSON-based schema in the database. And that does not directly map to any data schema format that Salesforce provides today. And so what is required to connect that data is you synchronize with Heroku Connect into a Postgres database. And then for our use cases, we are writing basically shell scripts that just use the SQL or the PSQL command in order to select data out of the Heroku Connect tables and save it as JSON. Postgres is really great at handling JSON. And so basically, you can just select stuff out of Postgres, save it in the right format as JSON, and then use the PIO import command line tool to actually import that data into the event store. And so the Buildpack, we have built hooks into it to help you. You can commit a script. And if you follow through the Buildpack directions, it'll lead you through this. But essentially, you commit a script into your repo, call it create sync events or create initial events. That's where you essentially use Postgres, use PSQL to select your data, save it into a JSON file, and then the Buildpack will automatically pick up that file and load it before it trains the engine. So that piece of the data connection is necessary. There is great hope that one day we can have some more magical graphical interface to map your data in. But this is the reality of the way a machine learning algorithm works when you want to have a fully customizable, programmable framework. OK?
Great session, really clear, thank you.
Awesome.
Can you speak directionally about any of the plans for the other templates? I noticed in the PredictionIO site, there's a big range of existing templates. Are there any directional plans is someone maintaining those from an open source standpoint, taking pull requests? Is there any plans to bring them as build packs?
Right. So it's a really great point. So yes, the Apache PredictionIO site has a gallery of engine templates. And that gallery of engine templates, after using it a bunch, I would kindly say it feels like a kind of experimental land, right? The templates you find there are frequently not full of best practices. They're more like just like, here's a quick way to show you how to use a given algorithm. The process of actually operationalizing that is not so direct. And so yes, we want to add more examples in the Heroku GitHub specifically. So right now we just have 2 that I demoed. We have some more cooking, but honestly, we come up against challenges with the framework, like when we try to do certain things, like we have a k-means clustering engine that we're working on. Trevor over here in the corner is actually working on it. And it's like essentially with that engine, we end up doing some things to write events back into that event store that aren't really sanctioned or supported correctly, so it makes it awkward to set up. So before we share things as Heroku optimized, we're trying to solve these problems so we're not just kind of throwing you to the wolves, you know? Yes?
Unfortunately, we're out of time for questions, but if you did still want to speak to Mars after the session, feel free to just come over to the stage, or we can talk outside as well. Thank you.